Um, let's see. So this is optics for energy, ECE 5962, 6962, MSc 5050, 6050. Okay, so I hope you're in the right class. My name is Rajesh Menon. That's my email address, bng.utah.edu, and that's my office. But I recommend emailing me rather than just showing up. So, and I'll be pretty good about responding if you have questions as well. Okay. The class, I've taught this once before. We're going to try something a little bit different this year. It'll be as project-centric as feasible, depending on how much people are interested in. So I'll go through some of the logistics today. We'll look at some of the introduction. Okay, and I'll walk you through the schedule and all that. If you have any questions, feel free to email me. Okay. Oops. So I'll post the slides also online, so you don't need to take notes and all that. I mean, you can if you want to. So let me. It's hard to see that. It's better, right? Yeah. So we're 1460. Tuesday, we'll meet Tuesdays and Thursdays, 12:25 to 1:45 or so. I don't have any specific office hours right now, unless if people are very much interested in that, I'm happy to do it. But in my experience, it's much easier if you just email me, and I'm happy to meet too when I'm around, as long as I'm around. Okay, so just note my email address. I don't have a formal textbook for the class, so you don't need to buy a book unless you have to. I mean, if you're interested, feel free, but you don't have to. I'll provide almost all the resources that you need, notes, mostly my notes, slides, all that kind of stuff. It'll all be posted online on my lab web page. It's very easy to remember, lons.utah.edu. It's not on there right now, so if you go on there, it's not updated, but I'll do it tonight. So you'll have all this stuff. Okay, so basic stuff. What are we gonna do? So my research area is optics, and I'm also interested in nanofabrication. That's not relevant here, not yet relevant here. Optics is the science and engineering of light. Okay, I'm particularly interested in the engineering because I'm an engineer. And in this class, we're interested in applying optics to efficient generation and utilization of energy. And it can be anything, as we will go through the schedule. Hopefully that's interesting, and we'll all learn a lot. In terms of learning objectives, it's useful to sort of stand back a little bit and think about what you want to get out of the class before we actually jump in, because we will go through a lot of math and all that, and you'll feel a little bit lost at some points. So it's always good to stand back a little bit and look at what are we doing here. I'll try to make that point, but it's useful for yourself to do that. So the goal, from my perspective, is to execute a project. And we'll talk about the various project options. There's a chair up here. 1, 2. Yeah, so just grab these. Just be careful with the camera. You can grab that chair too. Do you want to just put that down carefully? Just lift. Okay, lift that up. And I'll move that back. There we go. So as an objective, I'd like to be able to, each of you, in a team-based project, be able to execute a project, okay? And the idea is that we will try to apply as much as we learn. Obviously, it's not going to be perfect, because we're going to learn things which are a bit theoretical, but it's useful to understand. We'll try to apply, okay? And hopefully, we'll learn more than the sum of the parts, some of the lectures, right? So getting insight, understanding, not just on the technology side of it. I'm also interested in things which are not necessarily technological, but can you commercialize it? Can you apply this in various situations, as you will see when I talk about the grading to become a parent? So I want you to think in a very big picture point of view, you need to understand the technical aspects of it because this is an engineering class. But I expect that all of you to have a broader perspective, hopefully at the end of the semester. That's all. We should have high hopes here. Become familiar with the fundamentals of optical design and engineering. We'll go through some very basic things, fundamental ideas of how do you design systems, optical systems, and so on. And it'll become apparent why this is useful for some of the things we're going to talk about. Okay, and the last point I want to make aware is that we should be also sort of knowledgeable about what's coming out in the future. And I'll show you a little bit in the schedule, but what are the new technologies that are coming out? Not necessarily just related to the particular optical engineering and design that we'll talk about, but what are the new and exciting areas of research? We will also touch on them. Okay, so those are sort of the learning objectives. So hopefully we'll meet some of these, or if you're if you guys work very diligently, meet all of these. We'll see. Okay, the specific topics of interest. Okay, we're out of chairs. Do you want to go next door and grab a chair? Sure. Or just from outside. The specific topics, we'll go through it in a bit more detail as we go through the schedule. We'll talk about optical design. And primarily, I'm interested in non-imaging optics. And by that, what I mean is, how do you take energy from one location and assign it to another location? Okay, as opposed to imaging optics, where you're trying to take light from one point to another point. Okay, here we're going to talk about volumes and regions and so on. That's a little bit mathematical. We should sort of jump into it a little bit and try to understand it as best as we can. But again, like I said before, we need to always stand back and kind of see what that means. I mean, you will see when I talk about the grading where I'm going to emphasize. I'm very, very clear, so it should be obvious to you. This is an optics class, but we definitely need to understand the thermodynamics. Because without understanding what happens to the light or what happens to the heat, it's a little bit immaterial to design. I mean, you're kind of, you're doing the design with one hand tied behind your back if you do that. So we need to kind of think about the whole system. I'm not an expert in thermodynamics, but this is very basic stuff. So we should all be able to understand this. Okay? I mean, you have seen this before. It's mostly a review, but review with very specific applications in mind. So keep that sort of in your view. In particular, like I said, we will look at solar thermal devices, photovoltaic devices, things like that. Photovoltaics is solar space. We'll talk a little bit about the physics of these as well. Hang, you may want to grab a chair outside. The third point here is novel approaches to light management and photovoltaic devices. And these are aspects of areas of research that are emerging. There's a lot of interesting work going on, and we'll try to survey that a little bit and talk about some very, very exciting stuff that's coming out of labs from around the world. Okay, and that should be quite fun, hopefully towards the end of the semester. And emerging areas of other areas of relevant technology. This also addresses older technologies as well. That's why I kind of picked that up. Novels, not necessarily applicable. But. So it gives you, again, a very broad idea of what we will cover in the class. Now, in terms of, I must warn you, like I said, again, to underscore, we will go through a bunch of math. So it's going to be, some of the lectures are going to be fairly intensive in math, but like I said, it's not terribly difficult, and it's something all of you should be able to go through. I mean, you're all seniors or graduate students, I assume. This is probably a good segue to all of you to very quickly introduce yourselves. Okay, very briefly say your name, what department, and whether you're grad or undergrad, so everyone kind of gets a sense. Just stand up. Why don't you start?
My name is Faisal Chaudhry. I'm from the Electrical Engineering Department, and I'm a PhD student.
My name is Vana Masid. I'm from Electrical Engineering Department too, and I'm also a PhD student.
Mac from MSc, and I'm also a PhD student working in solar cells.
Ram, electrical engineering, and I'm an undergraduate, hoping to take this as a graduate class.
Trevor, electrical as well, and just doing grad work.
Are you a senior?
Graduate.
You're a graduate. Okay.
I'm Shayan. I'm from ECE undergrad.
I'm Apratim. I'm from ECE as well, PhD student.
I'm Xiaoen from ECE department, PhD student.
I'm Trevor Dick. I'm a math and physics undergrad, and that's it.
I'm Jinjin from ECE PhD student.
I'm Tyler Hafen, and I'm MSc undergrad.
Ryan Snowball, MSc undergrad.
So from MSc graduate student.
Okay. Ben Bunnis, MSc grad student.
Eric, physics and math undergrad.
Hallie Allred, electrical engineering undergrad, senior year.
Longshan, ECE, senior year.
Dan Jacobs from MSc. I'm a grad student.
I'm now from MSc. I'm a PhD student.
Okay.
I wanted to say quality ECE, we are students.
I'm Zhongzhi, MSc grad student.
Xiao Yulei, MSc graduate.
Okay.
Peng Wang, EC department, graduate student in document group.
Okay, good. So we have a pretty nice mix. Looks like
I'm Jake.
It's
okay.
Sorry,
No, it's okay. I'm Jake. I'm a grad student from the University of Oregon, and this is the last class I'm taking to transfer back over for my applied physics. So the program is device processing, semiconductor device
You
processing.
emailed me. I remember.
Yeah,
Yes.
yeah.
Okay, good. That's a nice mix. The reason I went through very quickly, by the way, is that the majority of the grading, as you will see, will be based on team-based projects. And I'm going to assign the team, so it's not like you can pick your friends for a variety of reasons. It's important that you learn how to work together. I need to, how many students? 1, 2, 3, 4, 5, 6, 7, 8, 9, 24, okay, that's good. So about 8 teams, three per team, roughly. Anyway, so let's keep going, so that's good. Okay, there we go, grading. So I'm very specific, very, very clear. So if you have questions, feel free to ask me now. The grading primarily based on team-based projects, which is why I put it up there. So 50% of the grade will be based on 5 mini reports, and I call them mini reports because they're only 3 pages, and you cannot go over. I will only read 3 pages and grade you on them. Okay. The deadlines are extremely important. So I'm going to give you the deadlines today, so you'll know exactly when you have to submit. Okay, the dates are all fixed, mapped out for the entire semester. If you have very specific excuses, I'm happy to talk to you about it. So there are 5 reports, 10% each. Okay, so it should give you an idea of what you have to do. And we'll have a mid-semester presentation. This is right before the fall break, and I'm going to give you the dates as well, right here in the class. Very brief, about 10. Since you have 8 teams, you'll have about 10 minutes per team. Okay, and again, you cannot go more than that. Okay, something like that. So we'll talk more about it up to 10%. And this is actually quite important. I'm going to emphasize about 20% of the grades on a submission to this National Clean Energy Business Plan competition. And I know this is a little unusual for an engineering class, but I think it's important for you guys to think not just on the technology, but how it can be implemented. Okay, and because you're all senior, I mean, you've gone through at least 3 or 4 years of engineering school, it's a good time to do this. Submission, by the way, is not due until April. So for those of you, and I'll talk a little bit more about it, this is a submission to me, so I'm going to grade it. For those of you who are extremely interested in pushing this forward, I'll be more than happy to help you, okay, if you are interested in actually going to the national competition and all that. I'll talk a bit more about it. The submission itself involves only I believe, 2 pages of an executive summary and a 5-minute video. Okay, so fairly straightforward. I'll talk about what that entails. Okay, so the technology is certainly important, and I will emphasize the grading on that, but it needs to be in a context on where it's being applied. Okay, and I'll talk a bit more about it, but always keep that in mind. And of course, we'll have roughly 20% on the class quizzes, and these will be very short, like 10, 15 minutes. So now I haven't scheduled them yet, but I'll give you enough notice. Okay? So, any questions about this so far? Again, feel free to interrupt me if you have questions, okay? Yes?
The mini reports, like each team member has to write one?
No, one team per report. Okay? And I will figure out how to grade individually because I will be talking to the teams individually. Okay? We'll be interacting a lot. So,
Quizzes are team quizzes?
no. But they're open book. They'll be here. You can open internet, whatever. Okay?
No book, correct?
No book, but I mean notes and whatever you need to access. Okay? Again, I'm not here to give you a bad grade. I'm here to make sure I know what you're learning or not. Okay? That's my goal here. I'm not here to give you a hard time. So again, keep that in mind. We're all here to learn, so hopefully we'll make an impact here. Okay. I'll talk a bit more about it. Any other questions before I go on? Okay, good. Questions are good, by the way. Feel free to ask. It's important that you ask, otherwise you won't learn. And also, if you don't want to ask in the class, feel free to email me and ask me later. Okay, a bit more about the projects. So there are 3 students per team. I'll assign them. Okay, from the list, by the way, that you're filling out. Hopefully, fill out. We'll talk a little bit about some project topics in a minute. Project deliverables, and briefly about the clean energy business plan, and the mid-semester presentation. So these are sort of the deliverables for the class, in a sense. Okay. Now, the projects themselves. Again, this is not necessarily an exhaustive list. This is something I'm interested in. I just put them up. As I mentioned down here. If you guys are excited about something, that's much more important than what I put up here. So come talk to me, email me, okay? And I'll be happy to accommodate you within reason, obviously within the scope of the class, right? So I put up a bunch. I'm particularly interested in this course on technologies for the developing world, but it doesn't necessarily have to be restricted to that. Okay, again, it could be applicable, for instance, in the outdoor industry or whatever, right? Solar cookers, things like that. So, again, however your interests are direct you. But I will guide you if you don't have specific interests in mind. So I put a few things up. Solar cookers. We'll talk a little bit about it today. Primarily, obviously, in this class, we will focus on the optical design. Can we do something clever? Things like that. Okay. Solar water pasteurization, which essentially means can we kill bacteria and things like that in water, make drinking water available. Water desalination is obvious to most of you, I assume. And there are several technologies out there, and we'll talk a little bit about that. Again, I will provide resources, reading resources for you to understand all the different technologies out there, and I will emphasize mostly the optics. Okay, so I mean, obviously, I will talk a little bit about devices themselves, but in the interest of time, we have to pick and choose. So you will have to do a lot of the background research yourself, especially for your project. We'll come to in a minute. Then a few other things, solar refrigeration, which is actually pretty fascinating, and I wasn't terribly aware of what's going on out there until I started reading about it. So there's a lot of very interesting stuff going on there. Maybe daylighting. What does that mean? That means can we take sunlight into incorporate it into architectural designs and so on, so we can get more natural light? And obviously it is happening in much of modern building and so on, but can we sort of apply this in a cheap, sustainable manner in the developing world? I don't know the answer to that. So I mean, things like that would be interesting. Water heaters, and solar water heating is actually a very, very big market, especially in Europe and the Middle East and so on. So it's there's a lot of interesting innovations maybe that could be done there. So it's something we would look at. And finally, photovoltaics. Photovoltaics, solar cells, and they're growing pretty rapidly, becoming very important around the world. And in particular, we will deal with concentrated photovoltaics, which means can we collect light in a very efficient manner and assign them to the solar cells. So we can access that energy in a much more efficient manner than could be otherwise done. Okay, and we'll talk a bit more about it in the class. Also, another thing in photovoltaics is in the emerging areas of research can we do light management? Can we, once the light enters the solar cell, can we do clever things to it to make it be absorbed in a more efficient manner? And we'll talk a little bit about that as well. So there's lots of very, very exciting research going on in that field. My group as well, but also around the world. Again, like I said, if you have specific ideas in mind, I would be happy to entertain those. So feel free. You should try to come and talk to me this week, if you have, because I'm going to assign projects this weekend. Okay, so keep that in mind if you have any specific ideas. Ideally, the sooner the better. Okay. In terms of metrics, I'm personally interested in application in the developing world, but that doesn't, like I said, doesn't constrain a particular application, because if you can come up with a clever application which could be implemented in the outdoor industry for camping, whatever, or it could save fuel costs, whatever, it's certainly quite important. And if you can think about how you would implement, how you would get it to the market and things like that, that's certainly a very, very important project. So definitely, this doesn't. This again, don't consider this as a limiting factors for the project. Okay. But in terms of the developing world itself, we need to worry about a number of very, very unique factors, and I'll talk a little bit about those also. Cost, clearly, because needs to be affordable. Durability needs to whatever we build needs to survive in pretty harsh conditions, in humid conditions, high temperature, dust storms, whatever, rain. Storage, sometimes space could be an issue. Maybe also size and so on could be important for transportation. You need to ship things somewhere. So there's lots of very, very interesting and very diverse set of considerations that need to go in when you think about designing devices. And obviously, these are also important for conventional markets as well, not just the developing world. But clearly, if you can address this for the developing world, you can obviously address this for the developed world as well. So I think they're in general useful. A lot of these technologies started off in the 70s, and they had a lot of trouble in the 70s and 80s being adopted across the world. And we'll talk briefly about it. And much of that had to do with cultural factors. So people were not appreciative of what people were already doing and what could be the obstacles to adoption. And this is sort of something, as an engineer, as engineers, we never think about them, but it's quite important that we do, if you actually want your technology to be successful. So again, this kind of stuff, I think, is something you need to think about. Right from the technological point of view, as the first, even as you do your first designs. Ease of use and climate conditions are this. Okay, project deliverables. This is probably the most important thing for you guys. Okay, so this is a list of 5 mini reports. And I listed exactly what you need to do, irrespective of what project you choose. And these are the exact dates that you need to submit them. And I need to receive them by midnight that day, okay, by email, preferably. You can print it out and drop it under my office if you have to, but, okay. The first mini report is due September 13th. A couple of weeks. Okay, 3 pages. Essentially, it's a literature review of your technology that you picked for your project. Okay, what's out there? Discuss pros and cons of the existing approaches. Comparisons, overview. Okay, very straightforward, very clear. If you're not clear, let me know today. If you have any questions about this, okay, because the clock starts ticking today, or as soon as I assign the project, which will probably be this weekend. Okay. The second report is due October 4th. Okay, and this is basically probably the most important part of all the 5 reports. Okay, it's your idea. Here, you have seen what's out there. Think about what you can improve. Okay, and this is obviously your chance to be creative within the laws of physics. Be bold, take risks. Think out of the box, hopefully, as they say, right? And obviously, you need to try to brainstorm with your team, maybe brainstorm with others. Email people, who are in the field. Talk to me. Okay. Again, just 3 pages, but outline your idea. Maybe some figures. Try to be as clear as possible. Then the third report is a plan. How will you implement this? What will it take? What are the steps you will take? So almost like a proposal. Okay? What are you going to do? And again, it depends on what you pick. You will have a whole host of technological issues, materials issues, cost issues. All of these you need to research a little bit. Again, those are due October 25th, so you have 2 weeks, 2.5 weeks. Okay. So again, a budget would be useful. How much would it take to get to a prototype? And if you want to be really ambitious, how much would it take to do manufacturing? Think along those lines. Okay. Again, in your idea section, I would prefer it if you try to think from the optics perspective. Again, I'm not going to constrain you to that, but you need to emphasize the optics. Clearly, that's part of the class. But it needs to fit into the bigger picture. Okay, and we will talk. We'll have interactions along the way. It's not like I won't hear what you're doing until then. Won't be a surprise to me. Okay, so make sure you communicate with me. It's quite important. I will talk to each of the teams. The fourth report is a bit more technical details of your idea. Whatever you propose in the second report, you're going to dive into it a little bit deeper. And by deeper, I mean you can do anything from simulations, optical design simulations, or CAD design simulations, whatever you want to do. And we'll talk a little bit about optical design software in the class, but whatever you want to do. To maybe even a build out, a demo if you are so inclined to it. You don't have to, but that's also a possibility. And that is due November 20th. Okay, so they are kind of dispersed, as you can see. The last one is the business plan with the commercialization strategy. This will be a traditional business plan with not just the technology, but also a small discussion of the market. And we will have a lecture just on the commercialization of it from the technology commercialization office here. So you will know exactly what you need to do. Okay. And that's due the end of the semester, December 6th. Okay? Again, like I said, deadlines are important. Each day you're late, about 10% of that report grade will be remote. Okay, so try to be as diligent as possible. Obviously, if you have very specific reasons, you got to let me know as early as possible. Okay? Don't tell me the day before. Okay? Any questions? This is important. I want everyone to be very clear on what I expect.
So So this is a team project?
Yes, it's all three people per team,
Three
roughly,
people,
yeah.
So people send out one report to you.
Yes, one report per team. Okay, no questions, that's good. Brief note on the clean energy competition. This is kind of it was run for the first time last year. It's run by the U.S. Department of Energy. The way it works is that the national competition is conducted in Washington, D.C. They fly you up there, and it's a big deal. Secretary of Energy is there and so on. Significant prizes, all that kind of stuff. And it's organized as regional competitions, so the different regions have local competitions. So the one for our region is in Boulder, Colorado, at the University of Colorado. Their Clean Tech New Venture Challenge, and you can go to their website and get the information. For those of you who are interested, the submission deadline is March 3rd, but our deadline is December 6th, so it's the more important one, as I pointed out in red. Okay? What you need is not very much, which is, in my opinion, it's harder to write something short than long. So it's a good experience for everyone. All you need is an executive summary, which is 2 pages long, and it should involve what is the problem you're tackling, opportunity, what is the market strategy, how will you implement it, how will you sell it, some sort of industry analysis. Again, a lot of these resources are available at the university through libraries and through the business school and so on, and I will help you with if you are stuck. Okay, because this is also a learning experience that you should be aware of. Technical product description, risks, economics, and team. Obviously, what I emphasize is the technical part, the technical product description, which is why I put that in red. But you clearly have to do all of it, okay, for a full, complete description. 5-minute video pitch. They give you some descriptions if you go to the website, but in my mind, try to be creative. Can be a product demo, elevator pitch, slide presentation, whatever. But it's a video pitch, so you're not going to actually physically make a presentation to me. You're going to upload a video to my website or YouTube or something. And I'm going to grade that. Okay. Last part is an IP declaration. That's not so important for the class, but for this competition, it's important. And again, if you come up with some interesting intellectual property, new ideas, which I hope all of you do, then you will patent it if you're so inclined. Okay, and I will help you a little bit if you want. But for the competition, it needs to be listed out what's up there. Just be aware of it. For the regional competition, like I said, it's in Boulder. And one nice thing about this region is that the National Renewable Energy Lab is located here. In this region, it's in Golden, Colorado, which is just outside Denver. So they provide a lot of support in terms of technical support. There are clearly lots of very, very, very good people there, and also other kinds of resources as well. So just be aware of that, okay? Okay, now in terms of the course schedule, this is what I have. So I'm going to zoom in a little bit and go through it reasonably carefully. So it's fairly well set, but it's a little bit flexible because we may not make enough progress in a particular class, so we'll have to push ahead a little bit. So just be aware of that. Like I said, I'll try to post most videos online, so in case you're out of town or whatever, it's okay with me. Just make sure you look at it. Today we'll go through the overview of the course and maybe look a little bit into some of the project topics. Thursday we'll look a bit more into some of the other project topics, again on a bigger overview level. And starting next week we'll start talking about optics a little bit, solar radiation, some of the basic understanding the properties of sunlight, thermodynamics of sunlight. And some of this is important when you start thinking about designing optical systems, because you need to understand what you're actually designing for. Okay. We'll look at thermodynamics of solar heating and cooking. Again, very basic thermodynamics. And I wanted to get all this up in front because we need to kind of get this understanding before we jump into the projects, okay? Then we'll look at geometrical optics, which is something you should have seen before. Very basic stuff, but we'll go through it quickly. Then this is a very interesting topic I wanted to cover also up front, is optical design for material recycling. It's a very particular application of optics, which is becoming very, very important in places like Europe. And in Scandinavia, for instance, you can actually bring recycling materials without sorting them and put it into a machine at a supermarket, and it automatically sorts it, and it's based on a very interesting optical technology. And we'll talk briefly about that, just again to give you an idea of what's different kinds of applications that are out there. And I will emphasize merely the optics and the optical design when we talk about that. Okay. Then we're going to jump into a little bit of math. We'll talk about Hamiltonian and Lagrangian optics, which are the basic ideas of how to do optical design, especially for non-imaging optics. Okay, so we'll go through some of that. Rays and wavefronts, and that's when the first report is due. Okay. So the 5th week, I will be out of town, so we have 2 guest lectures. Okay. The first one is by Dr. Mohit Devekar, who's a scientist here at the U. He will give us a tutorial on optical design software. In this particular case, we'll take an example of what's called light tools, and you will have a computer that you'll have access to a computer with this software if you need to do simulations. Okay, so we'll have that. As I said before, we'll have a lecture by Frank Norris from the Technology Commercialization Office, where he'll walk us through the steps required to start a company, for instance, technology-based company. Again, this is quite important because remember, 20% of your grade is based on the business plan. So make sure you kind of get an idea of what needs to be done. Since I'll be out of town on September 25th, we don't have a class. So, and if we need to do a makeup class, we will schedule it later on. Right now, I haven't left it blank. Then we'll talk a little bit more about the optics. So this will be the core of the class, the optical design. So we'll go into some basic ideas of reflection, refraction. How do we incorporate that into optical designs? How do you use symmetry for optical design? We'll talk a little bit about attendue and phase space, and that's a little bit of an abstract concept, but it's actually quite important in many different kinds of optical engineering. And it's a little bit difficult to grasp, but we'll try to do our best. So that gives you an idea for the first half of the semester. Okay. Second report's due right before the fall break. Any questions? The next half of the semester we'll talk about mostly, we'll finish up a little bit on the optical design part of it, and then we'll look at emerging areas primarily. So the week after fall break, again, I will be out of town, so we have a guest lecture, primarily on the physics of solar cells. Okay, and week 9, Thursday, we don't have a class right now. I might still do a remote class. I'm not entirely certain. I'm trying to set up a webinar, like thing, because I'll be out of town. But I'll let you know if that happens, depending on how much progress we're making. Okay. Week 10, we will look at radiometry, photometry, radiation heat transfer. And this is also a little bit underappreciated area of optics. We'll dig a little bit deeper into the optical design for radiometry, photometry, and so on. Then we'll look at fundamental concepts of non-imaging optics, this idea of energy transfer from one volume to another volume. Okay. The one obvious application of non-imaging optics, for those of you who may or may not know, is design of luminaires. So things like designing luminaires for lighting and things like that. That's how people design, for instance, automobile headlights, things like that. That's all based on principles of non-imaging optics. And nowadays people are using all these principles to do better light collection for photovoltaics, for instance. Okay. So maybe there are interesting things we can apply these principles to, say, water heating or water desalination, and that's a very interesting area in terms of applications. We'll spend about 2 lectures on that. And then on November 1st, we'll have the midterm project presentations, which I mentioned before, and I'll talk a bit more about it later on in the class, but it'll be about 8 to 10 minutes long, 1 per team. That will be a physical presentation here, okay? And obviously that would be roughly a halfway through your project, so you would have made whatever progress you've made, you're going to report on that. Okay. Then after that we're going to talk since then we're going to talk more about the emerging areas of research. Okay. Statistical ray optics is actually a very, very exciting, it's an old idea, but it's being applied to lots of new and exciting devices. We'll talk a bit about light trapping, and then the week 13 we'll have guest lectures by James Nagel, who's an expert in this idea of light trapping and plasmonics. Again, a very, very exciting area of research. And applications. There's several companies which are trying to get these ideas to market. So we'll hear a little bit about that. The week 14 we'll talk about 2D concentrators, and by concentrators I'm talking about concentrators for photovoltaics primarily, but we can apply the same principles for water heating, desalination, pasteurization, all those things as well. Okay. Then we have Thanksgiving break. Note that one of the reports are due. I think the second last report's due right before Thanksgiving. Then we'll talk about spectrum splitting approaches, which are again very interesting ideas for increasing the efficiency of sunlight to electricity conversion by using optics. Okay, so for instance, light from the sun has many, many bands of spectrum. So it goes from the UV all the way to infrared, and all of this cannot be absorbed very easily in a single device. So the idea would be, can we optically separate the bands and absorb them in different devices? It turns out you can get much, much higher efficiency that way. We'll talk a little bit about anti-reflection coatings. This is an area of optical design which is quite important. Why? Because for instance, in a solar panel, you have a cover glass on top. Roughly 5 to 10% of the light can be lost because it's reflected off the top cover glass if you don't design it properly. That's quite a significant amount of loss. So you can avoid those losses by a proper design of the anti-reflection coating. This is important for glasses, for instance, people who wear glasses, windows, things like that. So it's a very, very diverse application area. The last reports due that day as well. That's November 29th. Okay. Then the last week of class we'll talk about concentrated photovoltaics. Hopefully talk a bit more about some of the very new projects which are coming on board. One of the largest concentrated PV plants are going online in California, like this summer. So we'll talk a little bit about that. So it's a very interesting area of research. And very, very big projects are being planned in North Africa and the Middle East and so on. It's going to be, I believe it's going to be quite important, so it's useful to think about it. Finally, we'll talk a little bit about solar simulators. And that's interesting because a lot of the device design, if you do go work for a PV company, for instance, involves working with solar simulators and other kinds of optical systems. It's actually an optical system. So we'll look a little bit into the design of these and gain some understanding of how to use them properly and so on. And finally, the last part of the project is due. That's the last day of class, December 6th. We don't have the finals. So. Okay. Any questions?
No final, you said?
No finals, yeah. You saw the grading, well,
yeah.
That's it. That's whatever I had is what you get. So.
When are you planning on doing the quizzes?
I haven't scheduled them yet. I will probably give you like 2 weeks notice or something. But the quizzes are short, so they will be 15 minutes long in the class, something like that. That's what I'm planning for. Maybe 2 or 3 of them. But they will be probably towards the middle of the semester because we have to go through some of the material, the technical material first. Okay. Okay, so I want to take the rest of this class today, talk a little bit about solar cookers in particular, and again, in a very broad sense about the different parts that go into it. And like I said, I want to use this week to talk a little bit about potential projects and different areas that require some innovation and some thought from a creative standpoint. But let's start with why technologies were developing world. I mean, I think the potential is pretty significant, and this has to do with the many factors, obviously. But the most common sense factor is that you have a very huge amount of solar resources in the tropics, which is where the majority of the developing world tend to be, with little access to infrastructure, roads, electric grid, and so on. So it's perfect in a sense for off-grid applications. I mean, off-grid technologies. Biomass is what's typically used in most of the world today for cooking and so on. And by that, what I mean is wood that's gathered, cut down, dry grass, things like that. So unfortunately, that's depleting really fast in majority of the world, and obviously they also contribute to CO2 emissions, which can be quite problematic. Again, if you just think about it from a market perspective, your impact as an engineer, the impact of the technology can be quite significant because you can impact, a quarter of the world. If you're successful, that's pretty incredible if you think about it. Billions of people, right? 1 out of every 4 people in the world have no access to electricity. So from a impact perspective, I think the potential is significant. Market opportunity, I think there are some interesting models for sustainable business development, for instance. How do you get these kinds of technologies adopted in the developing world? I think it's an interesting area, and lots of different things people are trying and failing and learning and so on. So it's something that we should all as engineers think about. If that's what you want to, if your goal is to have some technology out there. And it's something we often don't think about when we just look at the detail. So those are a few of the reasons I will put up. Now, I want to take the rest of the class a little bit and talk about solar cookers and what's out there. I'll give you a very, very brief overview. The reason I picked this primarily was because this is some of the most well-developed technologies. People have looked at this. Solar cookers have been around probably for hundreds of years. But more recently, technological implementation has been for a couple of decades, I'd say, at least. So let me just start with an idea of what is a solar cooker. And this is just a video I picked out of YouTube from, I'm going to zoom through from
installation of this sophisticated home automation system and technologically advanced switches and wiring and that sort of we just want to go live in a yurt. Hey, it's dark, showering in the river.
Sorry, I'm going to fast forward that a little bit.
And also connect us with her. Show you how it works here in a minute. But
all right, so this is a useful video that shows you the different things. So they're making some chicken thing, but first of all, the pot is black, right? And they put the food in the pot, and the pot is black because it absorbs the most amount of light, right? Of the sunlight. And we'll see some more details of the solar cooker in a second. That's what that is.
The solar oven.
Yeah, it's called the oven.
I always wear sunglasses when I do this because I do not like having that direct blinding light in my eyes. Take this, set it down in here. It will easily, in a few minutes, get to 250 or 300 degrees. We leave it here for about 4 hours, come back, and dinner is ready.
Remember, there are lots of healthy choices.
Okay, so there are a couple of things that are important here. to point out. First of all, you see these are folded. There's a panel reflector, right? Secondly, there's that thing that he pulled open. That's essentially an enclosure which creates a greenhouse effect. We'll talk about in a second when he puts it down close to it. Okay, a few interesting things there. Okay. So there are a number of different kinds of cookers, and we'll talk briefly about them. The first one and the simplest one is probably this, which some of you probably have seen, referred to as a box cooker. Essentially what it has is an inner box. It's a box essentially. It's enclosed with a top transparent aperture. It's typically glass or plastic, which lets in sunlight but keeps the heat in, and we'll talk briefly about that. The advantages are they're very simple to make. You might have made one in your high school projects and so on. And typically it also uses a reflector, which is shown up here, which reflects some of the light into the oven. So you increase the collection area in a sense. Okay? That's a very simple example of an optical engineered design. Okay, so you can, for instance, look at it and think, from an optics perspective, what can you do to improve its performance? That's the sort of question you want to ask in your project. I'm not saying this particular thing, but just an example. Then, obviously, insulation is quite important because the whole thing has to maintain the heat, right? The advantages are that they can be slow, even cooking. The disadvantages is it's very slow as well. Remember in the video, the guy said he left it there for 4 hours or something. So again, that's a trade-off.
Slow cooking is the best way to cook, though, right?
Yeah, some people might disagree because of the prevalence of fast food in this country. So, but yeah, I mean, it's a matter of taste, which actually brings an important point. A lot of times technologies work fantastic, but because people have very different tastes or requirements, whatever, they may not get adopted. So it's very, very important you understand what people want as you design your technology. It's something that's useful for anything that you work on as an engineer. One nice thing about these is that they're very safe. You don't get hot spots or anything, so you don't need to blind your eye. And they're fairly easy to use. Okay, you're not concentrating light too much, right? As opposed to the panel cookers, which is basically what the video had. And he had a panel on top of a box, so it's a combination. But in a regular panel cooker, all you have is just a reflective panel, which is usually folded up. And these are nice because they can be shipped around, they're very cheap. Usually it's just aluminum foil attached to cardboard or something like that. You can fold them in different shapes. Maybe someone can think of clever origami approaches to get the more light out of it. I'm not sure. Okay, so there's no inner box, very simple, very cheap. The simplest possible way to do it. Unfortunately, the structural integrity is not very good, so it can be unstable in high winds, things like that. You have very little insulation, so you don't necessarily maintain any heat. And if you're cloudy, you have issues and things like that. So, so if you're when you have cloudy, if you have a nice insulated box, obviously it can maintain some of the heat, right? So the sun can be in a cloud for a little bit, you still have fairly good heat. Obviously, if you're cloudy for too long, it'll lose the heat because it's a thermodynamic equilibrium, right? There's always heat loss, and you need to put in some heat gain as a balance that maintains the temperature. Okay. You can go a bit more complicated with these parabolic cookers, and they're fairly dangerous because you're collecting a lot of light, focusing to a small spot. You get very high temperatures very fast, and so on. There are several commercial solar cookers out there, which are like this, and they're primarily used for large volumes of food because you can collect over large areas and so on. They tend to be expensive. You can cook very fast because of the high temperatures. But remember, the way this works is this is a parabola. Remember, the parabola has two foci. This is the closest focus, right? So light coming in, it gets focused to one of the points, and you have all the energy concentrated there. That's where you put your pot or whatever to cook. So what does that mean? That means if the sun moves, that focus can shift, which means that you need to follow the sun, you need to track the sun. Okay, so that's kind of a trade-off, right? Because if you want something out there which is moving and so on, you have to make sure it'll last in dust and wind and so on. You don't want it to kind of seize up. That's an interesting design problem to some extent. Can you trade off the focusing versus the tracking, things like that? And they're expensive, more complex, harder to ship because they're big and so on. And obviously they have risk of fires and eye injury and things like that. They can get pretty hot. There's another technology out there which is referred to as the Fresnel lens cooker. So I'll show you that video in a minute, but it shows a couple of different devices. But this is sort of what it looks like. This is actually, I believe, a company in California which builds these. And it's essentially a Fresnel lens, which is that sheet of plastic or a piece of glass. Now, for those of you who may have seen, actually, we have one here. This is a Fresnel lens, right here. So you can, after class, you guys can come by and take a look. That's what it is, a piece of plexiglass, some patterns on it. All it does is it takes light and focuses it down. Much like a regular lens, but it's a very thin piece of plastic. The one right thing, it's right underneath this piece of cover glass right here. You can come up and take a look. And the nice thing, obviously, is that if you want to collect large areas, you can make a thin sheet of plastic, so it can be cheap, as opposed to a big volume of parabola or a huge lens or something like that, right? So there's some advantages. Unfortunately, it gets high at very high temperatures, just like the parabola, parabolic cooker can cook quickly, but again, it has the issue of tracking. You need to follow the sun, complex, and so on. Let me just quickly see if this, I don't know, fast forward through quite a bit of this.
You're cooking with green power science.
Let's see.
So I have some garlic that I'm going to be
Okay,
boiling the
so
water in this stainless steel cylinder that Dan made. He had it cut professionally and then inserted a wooden cork that he did all by himself. It's been tested out, it boils the macaroni beautifully, and because we're using the Fresnel lens, right here where the dark spot is where the sun is going to be hitting it. So I'm going to start right now, fill it up.
Forward that a little bit.
Okay. Now, I'll be walking over there.
So you can see where. So that's what that is. That's a Fresnel lens.
And it's going to be at a tilt. Rotated this Fresnel lens so that the side is getting all of that light.
So the bright area is where it's focused, more or less.
Okay, while that's doing its thing, boiling, I'm going to start the salting garlic. I have this stick, which I'm going to be placing
So this is
right
kind of an
here.
interesting thing.
And this lens is going to be angled so I know exactly where my temperature is.
So,
and as you can see, it's already
so
starting
it gets pretty hot.
the wood stick.
Because you're collecting light from a pretty big area and kind of focusing it
That's
down.
going to be a perfect
You see one interesting thing here is that it has
skillet, I put some olive oil,
in
and
a
it's
second
already
we'll
at
show
good
it.
temperature, so I'm going to drop in
See
some fresh
the-
garlic that I cut up. I use a lot, but you can always use a little less if you think it's too strong for you. Stir it around a little bit.
They'll show the bottom reflector in a second.
Just did the Fresnel lens, so that way we're a
Yeah,
little bit
so
closer
you
to our
can,
pan.
you're
And this
redirecting
here,
some of the light that's missed
place that way there's a
by the pot back.
bouncing onto the pan.
Either with just a flat reflector underneath, or you consider using a parabolic or whatever.
We're at
So
a great-
lots of interesting ways to apply optics in these kinds of things, and there's lots and lots of examples like this out there. So you should try to go look at and see what other people have done. Which, by the way, if in whatever technology you pick for your project, that's exactly what you need to do. Go see what's out there. Okay, what people have done. Call them up or email them. People are very, very happy to share their experiences with you. Okay? And think about and ask them what the challenges are. Figure out what the problems are. Can you contribute something to solve those problems? Primarily from the optics end of it. Okay? Now let's talk a little bit in the rest of the class about some of the heat principles. Okay? Again, this will be very broad rather than going into some of the equations, which we will go in a later lecture. For this particular example of solar cookers, okay? So first of all, there are three things that are important. One is you are gaining heat into the system. So you think about this as a closed system, so you're introducing energy in, you have energy loss, and a balance between these two creates a thermodynamic equilibrium which gives you a certain temperature. Right? And you're trying to kind of push that temperature up. That's basically the goal here. In this particular example, different things have different goals, obviously. Heat gain is essentially a greenhouse effect. As we saw before, we have a plastic or glass lid which allows visible light to go through, and that gets absorbed by the dark utensil, pot, or whatever, and typically re-radiates, right? Whatever absorbs will also radiate, but because it's a black body, it will re-radiate at a longer wavelength, right? And we'll talk a little bit about that also. But which exactly like the greenhouse effect, because the longer wavelengths are then reflected off the top. So the glass is transmissive to visible light, but reflective to infrared light, far infrared light. That's basically what greenhouse gas effect is. Right? Obviously, for the planet, it's the clouds and whatever particulates you have in the air. It's the same thing, right? And it's the same thing as some of you might have walked into a greenhouse nursery and things like that, right, where you grow plants. Same principle. The other important thing is that the absorbed energy must be conducted to the food efficiently. So that's another area of design, which is also important. Is the energy has to be conducted there and not conducted down to the walls or whatever, right? So which means you need insulation, all that kind of stuff, and hopefully better design. We'll talk about the heat losses in a minute. So I have a good class exercise for you. So I have box 1 and box 2. Which box will receive more sunlight? Why don't you talk to your neighbor on your left and discuss for a few seconds? Okay. Now. You're going to talk to me. Okay, let's stop. What about you? Let's see. What do you think?
We were just thinking that the flat one, or the curved one where it's perpendicular to the light coming in, would be better for transmission of light.
Yeah, that's correct. Now, remember, exactly right. The piece of glass obviously has the same area. That's where it's been drawn. The only reason you're getting more light through here, it has to do with the projection area, right? If you collect light at an angle, you will lose energy because it's spread over a bigger area. Okay? So, anyway, so you can imagine that, right? If you're orthogonal to the surface of the light, to the rays of light, you will collect the majority of the area. Otherwise, you have what's called a cosine error. You have a cosine theta loss here. This is this angle right there. Okay? Now, the second question, again, repeat the same exercise. Which box has more losses? Go ahead. Discuss.
I thought box 2, because it has more area.
More area.
More surface area.
Okay, yeah, that's right. Yeah, exactly. So, what does that say? That says you might be collecting more light, but you might be losing more light. So again, the lesson here is that we can't just look at one side of the problem. We gotta kind of think about the system to a certain extent. Right? So, for instance, I can't tell which one is better, right? You can't without knowing some detail. So the other important part in heat gain is reflectors, as we saw in the videos. You can have reflector on one side, which reflects the light in the morning, reflect in, or on two sides, which collects more of the light. Basically, what the reflector does, it increases the aperture area. And we'll talk about this primarily when we talk about optical design and so on. Okay? So again, that's an important criteria when we think about optical heat gain. Now, heat loss is the other side of the equation, as we just saw. And it happens in three ways, which we all know: conduction, radiation, and convection. Conduction happens in a number of ways, right? So the pot is hot, and if it's touching the bottom, it can conduct and lose the heat away, instead of just keeping it within the food. So typically what happens in these particular systems is you lift them up with an insulator and have the air act as an insulator, essentially, right? So you're not touching. You can have radiant heat, essentially. The radiation from the hot pot at longer wavelengths is usually trapped by the container, which is the glass on top, aluminum foils, which acts as a radiant reflector and so on. Right? It just tries to keep in, but it's not perfect, so you have some losses through the gaps and so on. Convection essentially means that heated air. So there's air inside, which gets hot, moves around, and you can escape through the gaps. It's taking the energy out. Just like in a house, right? Same problem. Okay? So we need to consider all these when we kind of start, if you start modifying the system in the optics, from an optical engineering perspective. Now, heat storage is clearly important. For instance, if the sun goes behind a cloud and things like that, then the thermal mass becomes important. Thermal mass is essentially the ability to retain heat, okay, which is why it takes a long time for certain things to heat up, but it will maintain that temperature for a longer time than other things, right? Water versus air, things like that. So that's an important design criteria which should go into it. Although, like that's pointed out, the higher thermal mass takes longer to heat, but it will maintain the temperature longer. And insulation. So very, very basic stuff. Now, in terms of materials requirements, it's useful to also sort of understand this. There are four things that we need to be aware of. Structural integrity, so we need to have some structure, some strength, right? You need to have some sort of support structures. People use all kinds of things, everything from cardboard, which is the cheapest possible approach, to metals, aluminum, all kinds of things, metals, bamboo, bricks, stone, plastic. For insulation, again, the insulation can go here, in the walls of the container, and also the top glass. So people use aluminum foil. Now, aluminum is not necessarily a good insulator, but it's a good reflector. So just put the heat back in. Right? That's the same function. Down feathered cellulose, rice hulls, wool, whatever. Transparent material is required for the top, and we talked about that briefly, glass, high temperature plastics. And in the US, most of you are probably familiar with oven roasting bags and things like that, which basically keep the heat in. The same principle. In fact, some of the low-tech solutions for this basically use those same bags, plastic bags, which get to be reused. Moisture resistance is sort of important, and we kind of overlook it quite a lot, because when you cook something in there, there's water vapor that's coming out, and you don't want the water vapor to just escape. For two reasons. One is you're going to lose energy, because it's just like the air is taking use. It's water, it's the same principle. Secondly, if water vapor escapes, and it can attack whatever material you have outside, especially if you're cardboard or something. So that affects the durability. So you want to have some sort of vapor barrier if possible. So some interesting things to consider. The other design considerations which don't fit in some of the previous categories are size, for instance. So, do we have the appropriate amount for food? Is it too big to be moved around? Can it hold whatever traditional cookware people are using, whatever, that kind of stuff. Sunlight collection areas, we saw in that quick example we looked at before. The larger collection area gets you higher temperature in general, as long as the losses are the same. Right? So you gotta kind of keep that in mind. Then Okay, so again, a couple of exercises. Is a square box better than a rectangular box? 10 seconds. Discuss.
Probably just the same.
No, with your neighbors. Why don't you discuss with these guys? First lesson.
The same perimeter?
Same area.
Same area.
Okay, let's see. Benjamin, any thoughts on this?
Rectangular.
That's right. Why?
It's longer. It's you can orient it with the sun.
Yes, exactly. Exactly right. Does that make sense? Again, we don't think of too much about it, but the sun has to come from east to west. So if you make it longer in one direction, it's easier to collect it in that plane. As opposed to if you put it rotational, right? You will get shadows on the walls. Very simple that thing, but it's an important thing, especially when you do optical design. Right? Next question, another exercise for you. Which direction should the rectangular box be oriented? This is really easy because I just answered it.
Yeah.
What is it? What would you say?
East-west.
Yes, exactly. Again, that's an important criteria when we talk about optical design. So when you design a solar collector, whether you have tracking, for instance, are you going to move it? If you're not going to move it, is there any way you can design it so you can collect most of the light during the day? And these are very important technological questions which have solutions to some extent. There are techniques we can use to address these questions. Okay? And if tracking is required, sometimes it is required. What is the best way to do it? Cost effectively, most durable fashion. There are lots of very, very interesting things that are out there. And I want, those are the sorts of questions you need to sort of explore in your projects. Okay? And analogous questions, not these particular ones. Okay, so before I finish very quickly, some of the challenges for adoption have nothing to do with technology, and I want you to kind of appreciate this as an engineer, as engineers, which I didn't until I read a little bit, and I'm sure most of us don't. Like I said before, these things have been done for a couple of decades, and they've failed quite miserably in the developing world anyway. People claim that the taste of food is different. I haven't actually eaten something cooked in a solar cooker. I'm not sure, but people claim that, and that makes a difference. Whether one obvious problem I can see right away is you have very little control of the temperature. I can't turn it down or up. Maybe there's a solution that we can come up with in optics, with optics. I don't know. But that's an interesting thing to brainstorm, for instance. Right? What about cloudy days? Right? How do you deal with it? You can obviously increase thermal mass, but that's kind of a brute force method, not so elegant. Is there better ways to deal with it? Cost, obviously, cheaper the better. One interesting thing, again, which I did not appreciate was disruption of traditional gender roles. What does that mean? That means in most of the world, the women gather firewood, they do the cooking and all that. The solar cooker, all that goes away. It's just automatic. It just happens during the day. So it kind of gives women more time, things like that, which tends to have disruption of traditional roles, which apparently have become an obstacle for adoption of these technologies. It's kind of interesting, which we never think about. So anyway, what I want to convey is that I think there are huge opportunities for us as engineers, new market opportunities as fuel prices rise, and interesting business models. Can you combine these things with innovations in microcredit, microloans, things like that?